Hello, everyone, and welcome to session 78 of the Porous Media Tea Time Talk. We are part of the Interpol Young Academy. We give the chance to early career researcher, PhD, postdocs to present their work to the worldwide community and Porous Media Research. I'm Sarah, and I will be your session chair today, and I'm joined in the studio by Perillo Santos from the Federal University of Cristoforo in Brazil. And today it's our pleasure to host two early career researchers, so Nathan Bernal from the Earth Science Institute of Orléans in France, and Karol Dąbrowski from AGH University of Krakow in Poland. So please join us in welcoming them. Feel free to engage anytime in the discussion. You can write your comments and questions in the YouTube chat at any time, because we will have Q&A session at the end of each talk. So without further ado, let me introduce our first speaker, Nathan Bernal. He holds a PhD from the Earth Science Institute of Orléans in France, completed under the supervision of Cyprien Soulaine and Sophie Romain. He worked on two-phase flow in porous media in the context of CCS, focusing on the pore scale and using a combination of microfluidics experiments, theoretical aspects, and numerical models. And this work has led to publication of one peer-reviewed paper, and another paper is currently in preparation on the effects of inertia during AIM systems. So his talk today will address the question, how can wetting film impact the stability of two-phase flow in porous media? So Nathan, thanks for being with us today, and the floor is yours.
Thank you, Sarah, for the introduction, and thank you everyone for being here today and listening to my talk. So yes, today I will talk about the impact of inertia and wetting films on the stability of two-phase flow with a pore doublet approach. So first of all, when we talk about two-phase flow in porous media, we need to introduce the Lenormand phase diagram. So this is for drainage. So my talk will be entirely about drainage, actually. So a non-wetting fluid displacing a wetting fluid. And so in the 80s, Lenormand and co-workers did the experimental study of two-phase flow drainage, and they characterized the drainage using two dimensionless numbers. First of all, we have M, the viscosity ratio, which is simply the viscosity of the injected fluid over the viscosity of the defending fluid. Defending fluid being the fluid which is already saturated inside the porous media before the experiments. And the second dimensionless number is the capillary number, which is simply the ratio of viscous forces over capillary forces. And based on these two parameters, they were able to describe the three distinct invasion regime. First of all, for high capillary number and high viscosity ratio, we have what we call the stable displacement or the compact displacement, where we have a smooth invasion front that displaces the wetting fluid from the porous media, leading to very little residual saturation after invasion. Indeed, we have almost none wetting fluid left behind the invasion front. Then, when we decrease the capillary number, capillary forces become dominant. And so only the biggest pore available will be invaded by the injected fluid, which leaves the smallest pores saturated with the defending fluid, the wetting fluid. This leads to a significant decrease in the displacement efficiency, as we have still a lot of residual fluid being trapped once we percolate our porous media. And then finally, when we decrease our viscosity ratio, we observe what we call the viscous fingering pattern, where we have this kind of finger-like pattern that grows from the inlet to the outlet, which leave a lot of wetting fluid behind the invasion front, which has thus a very poor displacement efficiency. And the exact boundary between these different regimes is somewhat blurry. It depends a lot on the fluid properties, on the porous media properties, the geometry of our porous media, and it's quite a problem because we need we want to characterize exactly on which regime we are, because this displacement efficiency is a really important parameter for many different applications of porous media. And so one of our hypotheses is that this uncertainty of these boundaries between the different regimes is caused by the wetting layers and the inertia of the fluids. Indeed, wetting layers during drainage were always present via what we call the Bretton films. Indeed, when we displace a wetting fluid with a non-wetting fluid, we often leave along the wall of a porous media a thin layer of wetting fluid, which can have an impact on the flow of the fluids. And finally, we have inertia. So usually in porous media, we work at really low Reynolds number, so we simply neglect inertia. But actually, during drainage, the invasion of our porous media is not a smooth displacement. It occurs via what we call end jumps, where we have the meniscus between the both fluid being pinned at the constriction for a certain amount of time before a quick and sudden invasion of the following pore. And during these end jumps, the velocity of the interface can be 10 up to 50 times higher than the average speed of the invasion front, which leads us to wonder, can inertia have an impact during these end jumps? So the big question that we'll try to answer today is, how does wetting layers and inertia impact the stability of two-phase flow in porous media? And so to answer this question, we will use a tool called a pore doublet model. So a pore doublet is quite a very simple porous media element where we have one inlet that separates into two different channels that then reconnect to form an outlet. This pore doublet is initially filled with wetting fluid, and we inject at a constant flow rate a non-wetting fluid to perform a drainage. And what will happen is that once the non-wetting fluid enters the pore doublet, we will have two menisci, one in each channel. And the relative position of this meniscus will inform us on the two-phase flow stability. Indeed, if both meniscus move at the same speed, it means that we displace entirely the wetting fluid from the pore doublet and we have no residual saturation. We have thus a very efficient displacement. But if one meniscus takes the lead over the other one, it can reach the outlet before the other meniscus, leaving some wetting fluid inside of our pore doublet, leading to residual saturation. Moreover, this kind of pore doublet are easy to put in equation. Indeed, they have quite a simple geometry. Moreover, if we consider that both fluids are incompressible, we have mass conservation. Since they share the same inlet and the same outlet, we have the same pressure drop in each channels. And this pressure drop is given simply by the sum of the viscous drop in the fluid number one, the fluid that we inject, and the fluid number two, the fluid that is already present in the pore doublet, and without forgetting the capillary forces. So from these principles, we can derive ODs that predict the meniscus evolution. I won't bore you with all the math, but basically, this kind of model assumes that inertia is negligible and that the viscous drop is given by an Hagen-Poiseuille law without taking into account the wetting layer that can and often will develop along the wall of our pore doublet, and capillary pressure given by Young-Laplace law. But how accurate exactly are these assumptions that neglect inertia and wetting layers? So to answer this question, we did some experiments in our own pore doublet. So this is what you see here. We have a pore doublet with symmetrical channel, meaning that each channel that you see here has the same geometry. And the particularity of this pore doublet is that the channels are diverging, meaning that their width increases from the inlet to the outlet. All the geometry, the cross-section of our pore doublet is rectangular. So uniform depth, only the width vary from the inlet to the outlet. And we perform drainage experiments with different kind of fluid so that we can match different viscosity ratio and different flow rates to have different capillary number. And we were able to retrieve three main invasion regimes. First of all, we have what we call a stable displacement. So you see both menisci move at the same speed, displacing entirely the water. So the water was the initial phase displaced by silicon oil, and we have no water left over in our pore doublet after displacement. Then when we decrease the capillary number, capillary forces become dominant, and we have what we call an unstable displacement. Only one channel is invaded because of the balance of capillary and viscous forces, which leave an entire channel entirely filled with water, which is thus a very poor displacement with a very poor efficiency. And then finally, when we decreased the viscosity ratio, we have the Safman-Taylor instability, which leads to a weakly unstable displacement, where we have one channel which is partially filled with a defending fluid. Very well, we were able to replicate this free regime without any problem. But now we wanted to use our set of ODEs that we derived earlier to predict in which regime we are, depending on the viscosity ratio and the capillary number. So this is what you see. This is our phase diagram with viscosity ratio on the x-axis and the capillary number on the y-axis. And here you can see the free regime that we just presented, divided by the theoretical boundaries that we derived using the set of ODEs that we have earlier, with stable regime at high capillary number, high viscosity ratio, weakly unstable at mostly lower than 1 viscosity ratio, and then unstable regime below for very low capillary number. And we can plot our experimental data on this graph, and this is what we have. So for most experiments, it works, but we have these two clusters of experiments that are completely mispredicted by our model, especially these experiments. So to describe it, we have black dot as stable experiment, blue triangle as weakly unstable experiment, and red squares as unstable experiments. As you can see, we have this cluster of weakly unstable experiments that theoretically, according to the model that we had earlier, should be stable. So how can we explain the difference between the experiments and the model? Well, we have to change the model. And for that, our hypothesis is that we need to take into account the impact of the Bretherton's films or the wetting layers. So how do we do that? So for that, we have Bretherton's law to correlate the width of our wetting films with the capillary number. And so we can see that we have a formula here. So we have these wetting layers with a certain thickness along the wall of our channel. And this will reduce the cross-section occupied by the non-wetting fluid, thus increase the meniscus curvature. We also have viscous coupling at the interface between both fluids, between the bulk and the films on the wall. That will impact the fluid flow, and we can revisit this viscous coupling using a partial slip at the wall. More about that later if you want. And taking all of that into account leads to non-linear effects on the meniscus dynamics. Okay, so now we have this new model that takes into account the wetting films. How does it compare with experiments? How can we verify that it actually does fit our microfluidic experiments? So for that, this is one of our experimental data. So on this graph, you have here on the x-axis the time, dimensionless time. In here on the y-axis, the dimensionless position of the meniscus, 0 being the inlet and 1 being the outlet. And what we see that this is an unstable experiment because only one channel is invaded. And from our experiments, we can extract the capillary number. We know the viscosity ratio, so we can replicate this microfluidic experiment using our numerical set of equations. And when we do that using our first ODEs that does not take into account wetting films, this is what we observe. So the numerical model without the film predicts a weakly unstable invasion, while our experiment is clearly unstable. And if we do the same thing with our novel model by taking into account the wetting layers, we have here an almost perfect fit between the experimental data and our novel model. So this led us to believe that taking into account the wetting layers significantly increase our capability to predict the invasion of a pore doublet. So with that, with this new novel set of equation, we were able to redraw our phase diagram. So this is what you see here. In black, you have the old boundaries between the different regime that we draw using the old model without the wetting layers. And in colors now, this is the new boundaries between the regime with a model taking account wetting layers. And what we observe is that this cluster of experiments that we could not match with theory before, we are now able to predict it correctly as weakly unstable if we take into account the wetting films. And additionally, with this kind of model, we are able to capture boundaries very similar to the one described by the Lenormand diagram between the free flow regime, which are stable displacement, capillary instability in red, and viscous fingering in blue. So this work has been published in October of last year in Advances in Water Resources. And I'm also working on inertia. As I told you earlier, during capillary dominated regime, the invasion is not smooth. It occurs via quick interfacial bursts, as you can see in these experiments at a low capillary number. And during these bursts, the velocity of interface is much higher than the average flow rate. So can inertia have an influence during these engines? To answer this question, we stayed with Porous model and we revisited the equation. Once again, I won't bore you with the detail, to add the inertia term in our equation. And what we observe is what you can see on this diagram. So in dotted line, we have the old model without any inertia. And in continuous line, we have the model with inertia. And we see that after each nth jumps, so these nth jumps are this sharp rise in the meniscus position. When we take into account inertia, we can observe this inertial oscillation that appear after the jump. And this inertial oscillation can alter the order in which the pores are invaded and thus alter the efficiency of the displacement and change the residual saturation after invasion. So we have this numerical model that shows that inertia is important, but now we need to compare it with experiments to verify if it works or not. So this is what we did. Same as earlier, we have here an experiment from which we extracted the displacement, the position of the meniscus in time. So this is what you see here on this graph in green and yellow. And we extracted the capillary number, the Reynolds number, and we use our numerical model with and without inertia to plot the theoretical dynamics of the curves. So in dotted line, we have our model without inertia. We see that it doesn't really fit with the experimental data. But when we use our model with inertia, this time we see a much better correlation between our experimental data and our theoretical model. So this shows us that taking into account inertia is crucial for correct prediction of the invasion when we have these end jumps present. So some take-home messages to wrap up this presentation. Porous models are simple but powerful tools to investigate two-phase flow in porous media, but the standard assumption of no inertia and no wetting films fails to reproduce our experimental data. So we need to take them into account to finally reconcile our microfluidic experiments with our numerical prediction. And that by doing so, we're able to reproduce the Lenormand phase diagram using a very simple tool that is the Porous. And that inertia, even though we usually neglect it, can have a profound effect on the stability of invasion during nth jumps. So if you want more information, you can ask it during the question. Or I have this publication in Advances in Water Resources that you can see if you want more mathematical derivation. So thank you for your attention, and if you have any questions, feel free to ask them.
Thank you very much, Nathan. So we will now open the floor for questions from the audience. And if there is any, we will start with some from here from the studio. So I have one to start with myself. So in your Porous experiment, is there a specific reason why you use like identical channels on the experimental setup? I'm asking because I'm thinking about extension to realistic porous media. For instance, if you have an asymmetric pore duplet shape, what would be the effect of the impact on the wetting film capabilities in this case? How will that affect your results?
Struggling to. That's a very good question. Actually, we started with the symmetrical power doublet because it was a publication by Aluceni in 2014, who theoretically studied this geometry that you can see here, and during drainage, and derived the equation to predict whether the experiment is going to be stable or unstable. That was at the very beginning of my PhD. So we had this all nice theoretical derivation, but no experiments to validate the model. So as a first step, we're like, okay, let's try it out. Let's see if it works. It's a very interesting experiment. It's a good start. And actually, we found out that it didn't match exactly the reality. And that's why we started to hypothesize on the impact of wetting layers and how it could influence the invasion. And actually, since the invasion of this kind of power doublet is an instability, because it's a balance between viscous and capillary forces, this small impact of wetting layers, which is usually neglected, can be seen as it can tip the experiments to being stable or unstable. So there, the very small impact of wetting layers can alter profoundly the stability of our experiment. So that's why we decided to use this kind of power doublet, because with high asymmetrical power doublet, it would be much harder to actually see the effect of wetting layers. And yeah, once we have that, it's a question of how to upscale it to more heterogeneous porous media, which is
but to upscale it to heterogeneous porous media, you will have to start with asymmetric power doublet geometries first. And fair. Nice. Interesting.
Thank you for your question.
Beria, do you have any question?
Yeah, someone from the audience question for Nathan. So let's hear them. Does it make sense to have the same study with a pore triplet or a pore quadruplet or pore n-pletted? What are the expectations?
So the kind of ODEs that we derived could easily be extended to a pore n-plet. We just dragged the equation much longer. But we don't expect a widely different behavior. If we have an unstable invasion, we will have the same thing, only one channel being invaded while the other one are not invaded. It could be interesting just to do it experimentally, just for scientific curiosity, but we don't expect to gain any more insight on the two-phase flow dynamics using a pore quadruplet or pore doublet. And since pore doublet are easier to image and to post-process, we stick with pore doublet. But who knows? Maybe there's something else unexpected, and that could be interesting to be done.
Mm-hmm. And regarding the upscaling, then do you have any insight on how wetting films are behaved in realistic features, or like do you expect it to have like a huge impact at the upscale level, or marginal one, for instance?
I mean, wetting films appears in drainage, but also during imbibition. At really low capillary number during imbibition, there is a certain regime where all the wetting fluid invade the porous media as wetting films along the porous media. So here it has a very high importance for invasion. It can also be really important for connectivity, because even if we have a pore that is filled with non-wetting fluid, if we have these wetting layers along the wall, we can still have connectivity of the wetting phase across multiple pores. So it has definitely a huge impact even in heterogeneous media. The challenge is upscaling it. Here we gave some law to predict how the non-wetting phase is going to move in the presence of wetting fluid, but it's some very simple geometry, rectangular shape geometry. On a real porous media, the pores are not that smooth. They are much more regards roughness, much more edges, which not necessarily with a 45 degrees angle. And so we expect actually the wetting films to have an even bigger impact on the flow. So of course, feeling it is hard, but I think it's really, really important to understand this phenomenon.
The audience is heated up now. Got a couple more questions. Talking about a real porous media, how would you expect your results to translate into 3D?
So to derive the equation, we also took into account the depth of our porous media, the depth of our channel. We are really working in a rectangular cross-section. So we are already somewhat in a 3D porous media. Of course, we have uniform depth. We make a lot of assumption according to a lot of assumption on the geometry of our porous media. So in a real heterogeneous porous media, the situation is much more complex, but definitely taking into account will have an impact on the flow, especially I think for inertia. Inertia is something that we usually neglect, but ants jumps are omnipresent during drainage. It represents up to 50% of the volume invaded during the drainage, and so taking into account inertia might be necessary to accurately predict the invasion. But imaging 3D is much harder than microfluidics.
So we have another question from Cyprian. So he's asking if you've tried volume of fluid simulations to compare with your experiments.
We haven't tried it, but it's a good idea. The issue is that meshing this kind of geometry is really hard because we need to have a very fine mesh near the walls to capture effectively the wetting films. And then we need to compare it to our experiments, but the experimental setup is never perfect. We already have some minor error when we make the macro model, and it's very complicated, but it could be a good idea to do this micro simulation at some point.
Yeah, especially moving towards realistic geometries in the end. That would be interesting to have this comparison.
Which is
great. Great. Yeah, I don't see any more questions from the audience. So I think we can move to a second speaker of the day. Thank you again, Nathan, for the very interesting presentation.
Thank you. Thank you for your question.
Very good.
Okay, while Karen is setting his presentation, I'm going to start presenting him. So, Karol Dąbrowski is an assistant professor at the AGH University of Science and Technology in Krakow, specializing in fluid mechanics and gas thermodynamics. His current research focuses on reactive transport of CO2 brine rock interactions due to CO2 injection, studying using high-pressure microfluidics and rock core experiments. He also develops advanced measurement techniques for subsurface gas monitoring, contributing to the next generation underground gas storage technologies. Today he's talking with us about gas-induced crystallization in brines, insights for porous microfluidics. So let me see.
So if you can share your screen,
yeah.
Then we will be uploading your presentation.
I share it. Yeah.
Oh, okay. Now I can see.
Now I'm here.
So, thank you for being us once again, Karol. The floor is yours.
Yeah, thank you for opportunity to give a talk. This work we do, it's mostly connected with the CO2 storage in reservoir as well as hydrogen storage. So I will show that whenever gas or fluid is used, we can study this feature. And I will mostly focus on first at the experimental part of the work, and then I will give some results, because the main idea is that we have the reservoir, so a big rock filled with brine, and when we inject either carbon dioxide, either hydrogen or methane or any gas, of course, big part of the brine is displaced, but there is some portion of brine which is residual, which cannot be displaced, but it will be evaporated by the gas flow. And when the brine is evaporated, at some point crystallization occurs, which can block injected well. And then our storage is just wasted. We cannot inject any more carbon dioxide on any gas. So we want to focus if there is any control of this crystallization, how big is crystallization, and what are their limits of the microfluidic, because still it's quite far away of big reservoir, which is like 100 meters long, for example. So our system, the basic system, is of course easy. We have the, of course, microfluidic chip. We use the chip which resemble rock structure, and then we have an injection part with a high pressure surgeon pumps. When first we inject the brine, so chip is fully saturated, and then we inject carbon dioxide or any gas. This brine is at first removed, and then the evaporation process starts. And then we monitoring the evaporation and crystal growth. And here are two images from microscope. First, it's a low resolution microscope, but it can give us the whole chip, right? The whole length of the chip. But actually, for this detailed research, we use this fast high-resolution camera, which gives us only like a small portion of the chip. So we just move the chip during the experiments. So we make a snapshot in the middle of the chip along the whole chip, and then we make an average. And the chip, we just bought it in some company. And the structure is random, but if we buy some bunch of the chips, the structure is always the same. So when we replace the chip, for example, we can break the chip because the pressure are usually high, like 5 megapascals, 10 megapascals. So sometimes we need to replace it, and we get the same structure. So it's very help us to compare results. So we will observe these high-resolution images. And here's the process, like snapshot of the process. First, we have our reservoir chip is saturated. So there is not huge difference between the glass and the pores, which is filled with a brine. And first, we have this displacement, this breakthrough displacement. It's very rapid. It's kind of seconds. When most of the brine is removed from the chip. So it's evacuated. It forms channels where gas can flow freely, but the rest, brine will stay there. It's rather do not move. Sometimes some drop can enter the chip and can go through, but rather they stay, the pools that are stationary, and they are just evaporating. And at some point, crystallization occurs, and this crystals grows, and the brine it's evaporating. And the second, it shows how we segmentate the image. So it's based on the color and intensity. When we subtract saturated image, breakthrough, dried with crystals, dry like fresh chip without anything, and we subtract imaging. So for example, like crystals are very intense white. So it's very easy to segment these crystals. The only problem is that some crystals are transparent. So we can capture, here is a segmentation, we capture on the boundary, but hopefully MATLAB has some library which can detect this boundary and fill the pores. And usually it's like 5 to 10% of the pores. If we would miss these transparent chips, it will give us error like 5 to 10%. And from brine, it's a different story. When we subtract, brine is just 0. It's very close to 0, so also it's kind of easy to segmentate brine. So we can monitor brine like every 3 seconds or 2 seconds. We usually use this time frame for measurement. And the whole measurement takes like from 1 hour till 15 minutes. And this is driving force of using microfluidic, because if we want to repeat it in the core, it would take days, for sure days or maybe longer. So we can repeat multiple measurements to make some statistic and to show impact of various fluids. And of course, to make this segmentation and, for example, to check multiple positions, we need very good positioning systems. So we have some step motors. It's not a big deal. And the first thing, the amount of crystals obviously will depend on how much brine stays after this first displacement. And this is a figure Nathan showed, because always gas and brine have very big contrast of viscosity. So always we have this fingering. Yeah? And this is snapshot, like first second of displacement, then second, third. And in fact, after 3 seconds, like most channels, they are connected. And of course, this path depends on its porous structure. So this is simply these glass pores. And the whole process like a couple of seconds. And the first question we want to ask, if there is a big impact of the saturation between, for example, for carbon dioxide, between phases. And for example, if we can modify, for example, surface tension of the fluid. So if we use not the brine, if we use some surfactant, if we decrease this surface tension, will it give impact for decrease of this brine saturation? Because for gas storage, we would like to have this brine saturation as low as possible. So here we show that this brine saturation versus real numbers, and there is slight decrease. But in fact, if we have the process with the same fluid, with the same flow rate, with the same temperature, this big randomness of the saturation. So this shows that this process is mostly random. There is the impact of flow rate, temperature, and so on, but there is huge randomness of the process. And we want to also compare with the fractal dimension the shape of the channel. And it seems that from one experiment to another, the shape is similar. There can be more brine, but connectivity, it's usually very, very similar. In 3-dimensional system would be very different, because in 3D, can be big pools with the brine which cannot be displaced. And in this 2-dimensional porous, high porosity system, the majority of the brine is always displaced. So it's a huge difference between these 3D, which we expect. And the first question we ask if there is difference in the saturation between inlet and outlet of the chip. And the statistical analysis shows that it's not big difference. And we could expect this, because in theory, at the inlet, it's a higher pressure, at the outlet, it's lower pressure. But because the chip is short, we don't see this huge difference in saturation. And then we use different fluids to show this saturation at the beginning. So we use brine with a different molality, its concentration of the salt. We use surfactant. This is acronym of the surfactant. We also decrease pH with some base solution. We use some alcohol which increase evaporation and also decrease surface tension. And we use ammonia, which increase evaporation, so this crystallization should be faster. And also modify surface tension. Of course, it depends both on viscosity, contact angle, but we put everything into at the end of the surface tension. So I will show the high surface tension situation. So we have big pools. Also, we have a droplets which do not fill the whole depth of the chip. And from the contrast for low IFT, for example, with this alcohol solution with a brine, we don't have much of these droplets. And also these brine pools are smaller. So of course we expect lower crystallization in these chips. So this is, even without segmentation, without any brief analysis, we can see there is this difference between these situation and how these crystallization progress. So with the time, the brine, it's of course evaporation, and the crystal, which is here, it's on the dark, it grows. And we have two ways of crystal growth. First, crystal can grow inside this brine, and usually this will be transparent, nice shaped rectangular crystals. But also we have this aggregation. So you can see that there is a crystal growth, but there is no brine. Brine is on the other side of the pore. So here there have to be a capillary flow, because salt is hydrophilic. There is capillary flow which feeds this crystal, and it can grow and clog the path. So we here show this clogging of the path. So in the real world, as this progress, it can clog the system, and this structure is like porous salt. With this resolution, we cannot see, for example, we cannot determine the thickness of this capillary film, nor we don't see the flow. We might expect that from other research that there is some small crystals also flowing, but here we cannot see this. And here, for example, this is a single crystal, a nicely smooth single crystal, which grows inside this brine, as we would expect. But it's like majority of the salt is like this. So this is some image that shows time evaporation. So of course it takes here in this experiment like 45 minutes, and brine likes to stay in this concave parts. So the shape really impacts the time of the experiment. Of course, flow, the higher flow rate, the faster is this evaporation, the fastest crystallization, but also the shape. And we check if these crystals grow random, but from one experiment to another, positions are different. There are some positions which are favorable. So usually here there will be almost always crystal, but some positions are random. So sometimes there will be crystal in another experiment, and there will be no crystal in this position, but at the end the total area will be comparable. So here's some bunch of results of the crystal fraction. So how much of the crystal stays after this evaporation. So it gives us information if there is clogging can be a big deal, or porosity will change more or less, because the lower porosity, the lowest storage capacity of the reservoir. And here we have these different brines. Of course, if there is more salt in the solution, there is more crystal fraction. So of course, these results is obvious. But also, if we use some surfactant or alcohol, which decreases this initial brine saturation, it also results in decreased crystal fraction. But for example, flow rate affects crystallization time, but it do not decrease the total amount of salt at the end. And here, compare the whole results. So we see this effect: the higher salinity, the higher crystal fraction, the lower salinity or lower IFT with alcohol, the lower is this crystal fraction. Also, we could check how big are these crystals, because small crystals won't clog the pore. The biggest crystals will clog a pore. So this average crystal diameter can also give that information if this clogging can occur. And here, the biggest crystals and biggest fraction gives us this ammonia because of the reaction that we showed later. So these things which were very interesting for us, because it's different process. It's not evaporation, but purely reaction of the ammonia, because we use ammonia water, so 25% of ammonia in water and the salt with carbon dioxide, which produce very rapid crystallization of ammonia bicarbonate. And if these crystals grow, they can grow as these star-shaped crystals. They can form long single crystal, and it works as a frame for brine. So it's caused that a lot of brine stays in the pore and cannot be displaced. So this is why after the brine evaporates, there is a lot of, at the end, of crystallization of this crystal, because the brine was trapped because of the crystals which grew just at the beginning. So in real world, if we have a rock which can have multiple elements, this reaction can occur. Of course, some crystals can dissolve because carbon dioxide, when brine form acid, some can precipitate. So for real world rock, it can be very, very interesting and problematic system that with the time different crystals can precipitate and dissolve. And the last slide is things which for me was striking. What if we use the old damaged chip? We cannot see that chip was damaged, but I use it for this ammonia, salt, carbon dioxide, acidic, and probably it destroys the surface, inside the surface of the chip. And normally process is that we have this huge, we have these crystals. The process takes minutes. And if we have this, let's say, damaged surface, a process, there is no crystallization for a long time. And then when first crystals appears, it takes minute, and the whole brine, it's evaporated, and the crystals do not fill the whole depth of the chip, but it grows on the surface. So maybe there are some, I don't know, because we don't have this kind of resolution, maybe there are some grooves which are filled with the brine, and the crystals grows very, very fast. Here was used hydrogen, which for this evaporation should be quite low, for sure longer than for carbon dioxide, but obviously this process was very rapid, 1 minute, and there is completely no brine. And I think it's because of this damage of the surface. So it shows that this glass, of course, it can be used for experiments. It gives a lot of information, but real rock has multiple elements, some chemistry, but also surface is never smooth. So maybe the process could be much, much faster than we expect from these microfluidic experiment. So thank you, and I'm ready for a question, and I will stop sharing. Okay, and I will return here.
Thank you very much, Karol, for the very interesting presentation. Again, we highly encourage the audience to post a question in the chat. And in the meantime, we will start with question from here. I do have one curiosity from my side. So it seems that from your experiments, the wetting properties of the porous surface play a role in where crystallization occurs, especially when you have aggregation outside the brine. And so do you see any aggregation patterns? How could you validate this hypothesis and quantify that?
Yeah, we only quantify with this wettability because we can purchase chip with hydrophilic and hydrophobic. So we make this comparison. For hydrophobic, there is less brine, less crystals, faster crystallization. So this gives us this hint about wettability, but the roughness can be really challenging. And actually, it's not rough, for sure not. And maybe we use this some kind of rock surface, which obviously was by Nora. Yeah, he's specialized.
True, because I'm having trouble understanding how crystal could aggregate to a microchip surface. To be fair, so is this
it's because the first crystal grows in the pore, and it's just suck brine all the time. It's sucking brine, capillary brine from any direction, and simply salt is growing on the salt, and this is why it's induced crystallization. The more salt, the faster is crystallization because we have more area which evaporates. And this is also, I will say, a big difference between the real reservoir, because in real reservoir we have the infinite brine supply, and the brine can really flow like hundreds of meters, and the crystal will grow infinity in theory, of course. And sometimes it's like presented from these carbon dioxide storage sites that it can grow in infinity. Here in chip, it will at some point there is no more brine. In the real world, there will be always at some distance there will be always infinite supply of brine.
Terry, do you have any question?
Yeah, I have one question. So it can be, I don't know, maybe a basic question, but when you say about crystallization, you're saying regarding only salt precipitation, or there's a hydrate formation there as well?
Here only we consider only this precipitation. In microfluidic, recently we know what is in the brine, so we know what kind of salt we didn't manage to, for example, distinguish salt.
Yes.
We know, for example, from the reaction that, for example, for ammonia there will be ammonia bicarbonate, but we cannot distinguish, for example, these two crystals now.
Yeah, that would be my
next question. We want to use Raman spectroscopy, but the chip, we have probably in our system it's not good for this because the chip is too thin and the signal is too weak. We hardly manage to get the signal from water and to point the crystal simply maybe because of our system. We didn't manage to pinpoint the exact crystal. So this is the crystal, I get signal from this crystal, and then move the laser and see, oh, this is different crystal. Yeah, sorry. The system what we have, we have a Raman for big rock, so we can, or for process rather some separator, big flow, and simply we couldn't put it to microfluidic.
Sure.
Yeah, you've got a challenge in your experiments between the field of view of your microscope and and the full scale of the microchip device, right?
Yeah, or use some polarized microscope. There are some microscope which can have this chemis, because they use for mineralogy, obviously. So
yeah. So you mentioned some positioning tool to deal with that. So this is to make sure like how the images are compared
yes. Because we have this
other.
system for microscope, but we have a RAM, either microscope, and it's hard because we cannot say where we point.
Interesting. Barry, another question from your side?
No, for now.
Okay. I still have a question regarding like, do you have any modeling tool to compare with your experiments, or how do you think you will be able to?
Not at all. My friends.
Okay, fair. Because I'm really curious about
so we hope maybe at the end of the year, we would like to combine these results with a simulation. It would be a big step, because then we can maybe upscale it to reservoir.
Yeah, no, and I'm actually curious how you will model like the aggregation in the non-brine area due to capillary effects. That would be interesting to see that.
Yes, and if we could support the constant brine supply, because then we can show that, for example, if we have brine at the outlet and the crystal will grow at the inlet, so it travels, for example, it's 1 centimeter, it will be really like proof that it can happen.
Yeah, let's have prospect for future research. That's right. Okay, so I don't see any question from the audience, so I think we can finish here. So it was a great session. Thank you again to both speakers for sharing their research with us today. It was great. And again, for the audience, feel free to leave any questions, comments, even if you're watching the recording. Like we always have a look on the comments afterwards. Next month's session is not fully set up yet, but we are hoping to hold a special session dedicated to the local organizing committee for the 2026 conference. So stay tuned. We will update you on when the session will be held. So this is us. If you have any comments, want to be involved as speakers, or subscribe to the mailing list to be aware of any new talk, just contact us at the Porous Media email address over there. Thank you, everyone. See you for the next Porous Media Tea Time Talk. Bye.
Thank you.
Bye.